Thank you so much. Can you hear me well? Yes. So before I get started, first I want to express my utmost gratitude and thanks to the organizing committee for keeping this wonderful series of conferences going strong and bigger, as it seems, every year. And in particular, thank Dennis for doing all of this organization over the past days. So thanks to everyone. I think they deserve a round of applause. Also, I wanted to mention that this work is joined with Elena and Molin, who are my two co-authors from the Federal Reserve Board. So the usual Federal Reserve disclaimer applies. So what is this talk going to be about? It's going to be about dynamic choice models. Okay, so our motivation is going to come mainly from empirical macro. So think about dynamic stochastic general equilibrium models. And in those models, we're going to work with a specific type of signal structure. We'll call the signal structure conditional Gauss Markov. So I hope you cannot recognize this name because we invented it. And if you can recognize it, that's very bad news, and send me the reference so I can be aware of it. Anyway, I will try to explain what these conditional Gauss Markov processes are. And the paper is going to be a very theoretical paper. So unfortunately, not even Monte Carlo simulations in this paper, not an application in this paper. This part of the work is only going to be focused on the methodology, on the theory. How do we actually solve these models? And then also something that applied macroeconomists care about, how do we find approximate solutions to these models that use a very popular software that empirical macroeconomists like to use, the Dynair software. And the Dynair, if you have worked with it, essentially tries to sort of implement the perturbation approximation to the model solution. So we want to provide some theoretical justification for applying the perturbation method to this class of models. All right, a very long explanation of the long title. All right, so as I said, our main sort of motivation comes from applied empirical macroeconomic models. And in those models, there is a widely accepted view that both time-varying economic uncertainty and agents' beliefs play a very important role in aggregate fluctuations. So macroeconomists have now long been interested in actually first writing down and then solving models in which agents have incomplete information over the model states and therefore have to form beliefs about those states when solving the model. So this, of course, raises the first theoretical question. How do we actually do that, right? So what are really the mechanisms by which we can solve a dynamic choice model in which an agent has incomplete information? That's going to be our first theoretical question. And then the second question is going to be more computational, more practical. Even if I know how to solve a problem in theory, if that solution method is not something that I can implement on a computer, that's not maybe very useful. So we're going to also provide some answers, sort of computational answers that pertain to the applicability of the perturbation methods to this class of models. All right, so there's a lot of different literatures that this is going to touch upon. So there's a long sort of list of macroeconomic models with incomplete information. Again, I want to stress these are the models in which the decision maker has incomplete information over the relevant states of the model. And you can find sort of, at least to the best of my knowledge, maybe first examples of that in the macro literature in the seminal Kidlin and Prescott paper. But there has been sort of a renewal of interest in these types of models which feature various kinds of news and noise shocks in sort of a series of papers in the years 2000. And I'm just sort of highlighting some of them here. I will have some more as we go through the talk. So this is sort of where the original motivation comes from. Where is sort of where our method is going to come from? Where is the math going to come from? It's really going to come from the control theory. So we're going to draw a lot on very classical results from optimal control. And in sort of maybe in his historical order, I would like to highlight this wonderful book by Charlotte Streibel, who has worked a lot on dynamic control with partial information. There's some very, very nice results there, although in a finite horizon setup. To the best of my knowledge, maybe the most complete treatment of optimal control under partial information can be found in this book by Bertzikas and Shreve that essentially covers infinite horizon case, general action and state spaces, right? So that's kind of the most complete treatment that we're going to draw upon. As I mentioned, sort of the second part of the paper will be devoted to the question of can we still apply the perturbation method to this model with incomplete information? So some of the sort of basics of perturbation method come from applied mathematics, and Fleming, this paper from 1971 is seen as sort of the seminal paper that showed how to use deterministic model solutions or solutions to deterministic model to actually approximate solutions to stochastic choice models. This paper has been written in continuous time, so it's maybe not very, very easy or user-friendly for the majority of applied macro literature. However, a lot of this work has sort of been translated into economics by Judd, who wrote a very nice chapter in the Handbook of Computational Economics about various kinds of approximations, smooth approximation methods, including the perturbation method. There's going to be some interesting results about what happens to our model as we drive all the stochastic elements in the model to zero. We drive the noise to the zero, and we look at the deterministic limit of this model. Why are we interested in the deterministic limits? Because again, the perturbation method is a method that says I'm using the deterministic model solution to approximate the solution to a stochastic model. So we're sort of interested what happens in this deterministic limit. And so I'm going to show you some results here, but there are a few papers again in control theory that look at this question in a continuous and discrete time setup. So these are some of the papers that I'm going to touch upon, and there'll be some others during the talk. All right, so what am I going to do in this talk? I opted for working with a very stylized and simple model for the talk. So I'm going to essentially take a macro one stochastic growth model, but with an information structure that looks like the one used in these two quite influential papers in macro. Instead, I could have given you sort of the most general setup. I'm not doing that in the talk, but that is in the paper. So you could replace this simple growth model with Stokey-Lucas, chapter 9, right? So if you live with Stokey-Lucas on a daily basis, you know, chapter 9, right? That's the chapter where sort of a lot of these results about how to solve these dynamic stochastic choice models are situated. What is really important is that in this paper, we focus on models where you have the right cardinality of the control variables and the endogenous state variables so that you can characterize optimality by an Euler equation rather than characterizing optimality by the Bellman equation, which doesn't require those cardinality restrictions. Again, we focus on Euler equations because macroeconomists really mostly focus on Euler equations, and then the perturbation method also works around the Euler equation. All right, this information structure, a la Cogley, Sargent, and Permiceri, actually turns out to be a special case of a larger class of nonlinear models, which we call conditional Gauss Markov. So I'll spend some time sort of introducing and highlighting the properties of this class of models. And so what we're going to do in this paper is essentially provide two results. So the first result is going to be saying something like this. If we don't know how to solve a model, a dynamic choice model with incomplete information, maybe we can try to find a full information equivalent of that model and then try to solve the full information equivalent. Right, so the first result of the paper is going to be to provide a full information equivalent of this class of incomplete information models that we consider, right? So it's sort of a very simple idea of saying, if I don't know how to do something in incomplete information, but I can provide something that's equivalent, where the solution to the problem is equivalent, and this equivalent formulation is full information, right? Then that can be useful. So, of course, it goes without saying that in the full information equivalent, the agent observes all of the relevant model states, right? So we're back in the usual kind of full information setup. Okay, so you will tell me, okay, but that's obvious how to do that. Actually, Bertsikas and Shreve already contain a lot of results about full information equivalence of incomplete information models. But the key property that we're going to drive from this conditional Gauss Markov structure is that our full information equivalents are going to be finite dimensional. Okay, so in general, obtaining full information equivalence is not very difficult, but they tend to be infinite dimensional. They tend to have states that are of infinite dimension. What we're going to show is that in this class of signals, those infinite dimensional states actually are characterized by a finite number of sufficient statistics. And so we're going to achieve this dimension reduction by exploiting sufficiency. Okay, so there are kind of two relatively standard ideas that we combine in this paper, right? Full information equivalence, that's the idea number one, and sufficiency as a way to achieve information, as a way to achieve dimension reduction, right? So we kind of put those two ideas together, and that gives us those finite dimensional full information equivalents. Okay, so that's going to be our first result. The second result is going to be to examine whether these full information equivalents can now be plugged into Dynair so that you can solve now your model using Dynair, maybe non-linearly. But this model, again, is a model that starts from an incomplete information setup. So in order to check whether we can plug in our model into Dynair, we really need to check the properties of this full information equivalent as the noise, the stochastic noise in the model goes to zero. And so the second result of the paper actually studies that limit. What happens when all the stochastic terms disappear? All right. So now you know what the talk is all about. You can go to sleep. I will wake you up at the end. All right. So this is the roadmap, right? So I will go through the macro one stochastic growth model very, very quickly and introduce this Cogley, Sargent, Permiceri information structure. Then I will tell you this is a special case of this class of models that we call conditional Gauss Markov. I will explain some key properties of that. I will go through the full information equivalence of my simple model, just so you see how it looks like in a simple case, and then I will discuss the perturbation approximation. All right, so this is again the most stylized, simplest sort of dynamic choice model that we could think of in the macro setup, right? So you have a representative agent, she chooses her consumption and savings, she maximizes the expected lifetime discounted utility, notice infinite horizon, and then she has some output and budget and capital accumulation constraints, right? So everything very standard. What is in red here is sort of the source of stochastic variation in this model is the productivity. And essentially, what's going to be very important is the law of motion of productivity that different works and different papers assume. All right, so we're going to follow, as I said, the laws of motion, sort of similar laws of motion that were proposed in these papers, two papers, which assume that the log productivity follows an autoregressive process, but with a random parameter, right? So there's a random autoregressive parameter, theta t, where this autoregressive process also has some conditional heteroskedasticity. So it has a time varying volatility. And we'll assume that this volatility is of the Garch type, right? So we're not going to go with the stochastic volatility specification, which is actually the specification used in these two papers, but rather we're going to go with the Garch type volatility. I will explain why when a little bit later when we define the general class of models. All right, so again, an autoregressive type model with a random coefficient. The coefficient itself follows an autoregressive type process here with a unit root. So the process is non-stationary. And we, in addition, have this conditional heteroskedasticity. All right, all the shocks in this model, all the epsilons are going to be IID normal. They're standardized, and we assume that the sequences of epsilons are independent. They're also independent of the first value, A0 of the log productivity. They're also independent of the first value, theta 0 of this autoregressive parameter. All right, so what is the sort of key difficulty? The key difficulty is that while the decision maker observes the log productivity, she doesn't get to observe this theta parameter. So there's an unobserved drifting parameter in this model together with this time varying uncertainty in productivity. All right, so the goal, right, is to first solve for optimal consumption in this model. And then second, to wonder whether we can approximate the optimal policy using the perturbation method, right? So those are two questions. So you may wonder, okay, why is the question not completely trivial? Why is it not completely obvious? Well, precisely because of this presence of one latent state in the model, right? So what are the model states? Lag capital and the log productivity, as well as this time varying random parameter, right? Those are all the model states. However, only two out of those three are observed, right? The last one is hidden, again, to the decision maker. All right, so what happens in models in which some of the states are hidden to the decision maker? We have already seen sort of a solution to this morning, right? The decision maker has to form posterior beliefs about that latent state, given all the observations, all the information that she has, right? And that essentially transformed this problem into an infinite dimensional problem, right? So the fact that we have to solve the model using the beliefs is something, again, that has been known for a long time, and it has been studied very well in a specific class of models that we call the LQ models, linear quadratic models. So those are models in which objective functions are quadratic. All of the other equations are linear. And so we know very well how to solve these types of models despite the incomplete information. And sort of the simple solution is to solve the model or find a policy as if the latent state is actually observed, right? So find a policy. It turns out that the policy is linear in those models. So find it as if the latent state is observed. And then instead of using the latent state, plug in the conditional expectation of that state given the information, right? So that kind of is what jumps out of the LQ setup. It's a very, very convenient result and extremely useful result. Again, comes from control theory and has had numerous applications in macroeconomics. However, if you have a nonlinear model, as I already said, right, the state becomes infinite dimensional. All right, why is this problematic in terms of the computation? Well, again, if you want to solve these kinds of models, right? So if, again, you're an applied macroeconomist and you just want to plug this into Dinaire, we actually don't know how to plug incomplete information models into Dinaire, right? So more sort of theoretically speaking, we don't know if the perturbation method, which is one, as I said, one big class of approximation methods to deliver approximate solutions, whether that method applies when some of the states are hidden to the decision maker, right? So all of the theory, or most of the theory, assumes that all of the states are observed by the decision maker, right? So there's also the issue of computation, right? So how do we actually come up with nonlinear solution methods for these models? All right, so as I said, what we're going to do in this paper is to say, well, if we don't know how to solve and calculate approximate solutions to this incomplete information model, maybe we can actually first try to derive a full information equivalent to that model, right? So the first goal is actually transform an incomplete information model into a full information model, and then use that full information equivalent to, again, get an approximation to the policy function. So apply our favorite approximation techniques to this full information equivalent, provided, however, we have established that this full information equivalent is in the right form to use those approximations. And so again, our first contribution is going to be to give you the full information equivalent and show that this full information equivalent is finite dimensional under this conditional Gauss Markov structure. And then the second contribution will be to really check that you can plug this into Dinaire, that this actually has the right form for the perturbation methods to apply. All right, so I talked really a lot about these conditional Gauss Markov processes, so I should introduce them. So let me actually introduce them by going back to the basics of the linear Gaussian state space models. All right, so let's start off with linear Gaussian state space models, right, in which we assume that our latent vector variables Xi follows a linear transition equation, right? That's the first equation. And what we observe is a vector which I call Z, which is linearly related to that Xi, right? Where we, in addition, allow for some constants, right, in this linear relationship. And where for, again, simplicity, but without loss of generality, we stack all of the epsilons, all of the shocks in the system into one vector of W's, right? So it's the same W that appears in both the transition and the observation equation. Okay, again, those who are sort of familiar with sort of some of this empirical macro literature will recognize the A, B, C, Ds of sort of standard linear state space models. Okay, so all of the W's will be assumed to be normal, right? They are assumed to be standardized. Again, this is without loss of generality because the covariance matrix of W can essentially be absorbed in B, right? So I can change B if I want to essentially work with W's that have a non-identity covariance matrix. The initial values of X's are also normal, and then the initial value is independent of the sequence of all of the W's. In this model, once again, only Z is observable, Xi is not. And this is a vector valued system, right? So all of these objects are matrices, they're of conformable dimensions. There are no dimension restrictions, right? So the NZ, NXC, and the NW can be different, right? So we can have different numbers of latent variables, observables, shocks. All right, so this is, again, a basic linear Gaussian state space model. What do we know about this model? Well, we know that if we take all of the X's from time 0 to time t, let's denote it Xi script t, right? And we take all the Z's, so all the latent variables, all the observed variables up to time t, then these two kind of vectors of variables taken together have a joint multivariate Gaussian distribution. Right, so in this model, everything is Gaussian. We have a joint big multivariate Gaussian. What do we get from this big joint multivariate Gaussian? Well, we get that all the marginals of these random variables are Gaussian, right? So C is marginally Gaussian, Z as well, but also all the conditionals are Gaussian, right? So latent variables conditional on all the past observations are Gaussian, and also next period Z's conditional on their past are also Gaussian, right? We get all of that from the multivariate Gaussianity of this sequence of random variables. All right, what else do we know about these conditionals? Okay, so they're conditional Gaussian, which means they have two sufficient statistics, the conditional mean and the conditional variance. But we know something else about these sufficient statistics. We know that we can update them in a Markovian way, right? So starting off with the 0 period conditional mean and 0 period conditional variance, as we observe our first observation, Z1, we're going to update Xi hat 0 and sigma 0 into Xi hat 1 and sigma 1, meaning the only thing that I need to calculate, Xi hat 1 and sigma 1, is the last period of those two objects, of the mean and the variance, and the new observation that came along. Right, so we have a Markovian property of these sufficient statistics. So this Markovian property is very important. Why is it very important? Well, because the Markovian or transitive, right? In some literatures, this property is called transitive, right? So this is sort of statistical decision theory literature, right? That uses this notion of transitive sufficient statistics. If you have Markovian or transitive sufficient statistics, then it follows that optimal controls are functions of these statistics, or in the terminology used by Blackwell, optimal strategies are memoryless. If you just remember those sufficient statistics, you can discard all of the rest of the memory. You don't need the entire history of Z's, right? Your optimal strategy is only a function of these sufficient Markovian statistics. Okay, so our big question is, can we find more general models, more general than this linear Gaussian state space system, in which we have the same Markovian sufficient statistics, like this conditional mean, conditional variance, right? Which would then guarantee that in these kinds of models, optimal controls just become functions of those transitive Markov sufficient statistics. And the answer is yes, right? And so the answer, what is this more general model, is it's this conditional Gauss-Markov model, right? So how is this conditional Gauss-Markov model constructed? Well, it's first a model where you replace all of the system matrices, right? A, B, C, D, and these vectors U and V by random objects, and you now allow them to be a function of the lagged observables. Right, so the key thing is They can be random. They are functions of other variables, but they have to be functions of observed random variables, of lagged observed random variables, right? So they're now functions, random objects, and functions of Z. And we assume, in order to get the Markovianity of the sufficient statistics, that they're in addition function of a statistic that we call here M, that has this recursive property of being a function of its own lagged value and the Z at time t minus 1. Right, so bottom line, A, B, C, D is still the representation. You could still talk about this representation as being an ABCD representation, but now ABCD and then U and V as well are random matrices that depend in a particular way on the past observations. They depend on Z and on one other statistic, which we call here M, that has itself this Markovian structure, right? It's only a function of itself and ZT minus 1. What are the restrictions that we need to put on these objects, given that they're now random objects? Well, we need them to be finite with probability 1, right? So we don't want things to explode for some values of Z or M. This M, again, is something that has to be observed. It potentially disappears from the model. So there are going to be some models where you don't need any M, right? So you have just A that is a function of Z. That's perfectly okay. So that's what I want to sort of capture by saying that the dimension of M can potentially be equal to 0, right? So M can potentially disappear. If you don't need it, you can drop it. However, we'll see that in a number of models, actually having this M is useful. All right, so what is the key property of this conditional Gauss Markov model? The key property is that these distributions of latent Xi given the past observed Z's are still conditional Gaussian, right? So we still have conditional Gaussianity, both of the conditional distribution of the unobserved Xi, but also of the one step ahead ZT plus 1. They're still conditional Gaussian. However, the joint distribution of all the X's and all the Z's is no longer multivariate Gaussian. So marginals are not Gaussian. Marginals of Z, marginals of Xi are very non-Gaussian. They're can be very asymmetric, very fat tails, very non-Gaussian. But what we maintain is the Gaussianity of the conditional distributions. Right? So what are we exploiting here? We're exploiting the fact that multivariate Gaussianity implies that conditional distributions are Gaussian, but this is just an implication. It's not an equivalence, meaning you can have models where you have conditionals that are Gaussian, but are not multivariate Gaussian. That's essentially where we're working, right, in this space. We're maintaining sort of a model that guarantees conditional Gaussianity, but the marginals now can be very non-Gaussian. In addition, because of this particular structure with these M variables, the sufficient statistics for these conditional Gaussian, right, the conditional mean and the conditional variance, when we add to them this M statistic, now form Markovian, a Markovian sequence, right? So a sequence of conditional means, conditional variance, and M's is now Markovian in a sense that if I want to calculate it at time t, the only thing that I need is ZT and the lagged values, right? So we again are in the setup where we have Markovian or transitive sufficient statistics. You wonder sort of how do we calculate these? Well, we actually calculate them by using the same Kalman filtering equations as in the time invariant case, but we replace all of these matrices with now random matrices, right? That are functions of the observations. All right, so now I think you understand where the name comes from, right? So we have models that produce conditional distributions that are Gaussian, right? So these are conditionally Gaussian models. They're a special case of a more general class of conditional Gaussian models that was to the best of my knowledge, first introduced in this book by Liptzer and Shiryaev in the late 70s. However, we added this additional structure through these M variables that guarantees the Markovianity of the sufficient statistics, right? So the added sort of part, right, then gets to the name of Gauss Markov. All right. Let me just, yeah, question? Yeah. No, no, no. They are measurable with respect to sort of z's up to time t, and not only that, but are actually functions of z and this m statistic. Yes, so they're not random once I condition on the past z's. All right, so some examples in 30 seconds. Gauss models are a special case of this. Regime switching models, where you switch regimes, but based on the observables, right? So not regime switching models driven by some unobservable switching variable, but regime switching models driven by observables, also special case of this model. Models with exogenously evolving time-varying parameters, right? So these random coefficient models that I had Cogley, Sargent, Primiceri are a special case of these models, right? Essentially, what you kind of write, you write this autoregressive equation for your observed z, right, which had a random parameter c. You write it as the observation equation of the system with a random observation matrix C, right? So having actually these system matrices to be random is really crucial in order to be able to kind of subsume or embed these models as special cases of this class of models. All right. Informational equivalence now in 2 minutes, right? So the idea is we want to provide an equivalent to this incomplete information model, such that if you solve the equivalent, you get the same policy function, right, as is the optimal policy function in the original model. But this full information equivalent has all the variables that are observed. How are we going to do that? As I said, the first step will be to say, let's characterize optimality of policies through Euler equation, right? So we work with Euler equations rather than Bellman equations. Then we sort of look very carefully, we inspect very carefully the Euler equation, and we realize that sort of the arguments of optimal consumptions, which in the general case are these posterior distributions of our latent variables given the observed information. And then the distribution that you need in order to calculate this conditional expectation, right? So what is in this information set and what is the conditional distribution that we need in order to evaluate this conditional probability? We call this conditional distribution control distribution, or the density, we call it the control density. Those two objects in the conditional Gauss-Markov setup are functions of our sufficient statistics, xi hat, sigma t, and mt, right? So we can replace wherever we had those infinite dimensional objects, right? We can replace them with these finite dimensional objects. Okay, so this gives us an Euler equation, an equivalent Euler equation, in which now the consumption optimal policy is a function of our finite dimensional sufficient statistics instead of the entire conditional distribution. And notice again, this conditioning, right, is conditioning with respect to the sufficient statistics, right? The two observed states, lagged capital and AT, and our sufficient statistics, which are sufficient for that control density that I defined in the previous slide, right? So the first step is actually rewrite now the optimality equation, the Euler equation, as a function of these sufficient statistics rather than these infinite dimensional objects, the filtering and the control density. But then we still need to provide the law of motion of these sufficient statistics, right, to close up the model, to give you a full information equivalent. So where is the law of motion coming from? The law of motion is going to come from the so-called innovations representation of this nonlinear state space model, right? So in this innovations representation, we're going to write how these conditional means and A's depend on their own lagged values, the lagged value of the conditional variance, and the new innovation, right, that is called here epsilon. All right, I have run out of time, too bad. But I will sort of stop at this slide, right? And I will say, you can trust me, you can feed this into Dynair, right? And that was kind of the whole purpose of this theoretical exercise, is to be able to say to my co-authors, right? If you rewrite your model in this way, feed it into Dynair, it will spit out a policy function, and that is going to be the optimal policy function of your original incomplete information model. If you want to check the details of that, you have to read the rest of the paper to check that the perturbation method applies. That will be for another time. Thank you. Thank you.